Boa tarde, Mochi. Boa tarde a todos. Boa tarde, Mochi. Boa tarde a todos. Boa tarde, Mochi. Boa tarde a todos.
Oi, pessoal, boa tarde. Alô?
Alô?
Boa tarde a todos. Estamos perto de começar a nossa palestra com o professor José Hamill. Por enquanto eu estou testando som e todas as coisas. Se vocês quiserem, tchauzinho, abrir suas câmeras, porque eu consigo enxergar vocês aí. Se alguém quiser aproveitar esse momento. Oh, look at this over there. Pessoal, vocês estão ouvindo bem a gente, que eu estou falando?
Sim.
Obrigado, cara. Aqui. Um pouco de ruído, Bruno? Puxa vida, e agora? Tá melhor? Eu fiquei longe.
Melhorou. Para mim, melhorou.
Eu também agora fiquei longe das caixas, né? Talvez isso melhore. Bom, quem tiver aqui quem está nos assistindo pelo YouTube, né? Se vocês quiserem fazer interação, por favor, mandem mensagens lá no próprio chat do YouTube. Quem quiser quem está na sala do Zoom e quiser interagir, né? Aí no final da palestra a gente vai abrir um momento para vocês falarem. Eu vou colocar algumas pessoas para me ajudar na admissão das entradas. Vou deixar você como co-host. Para também. E aí vocês vão aceitando as pessoas para entrar. Agora eu não sei se é a Juliana Amaral, que é a Juliana Amaral que eu conheço, bastante tempo atrás. Se for, bem-vinda. Se não for, eu não conheço, mas também muito prazer em conhecê-la. Seja bem-vinda também. Ushida-san, seja bem-vindo.
Fala, Mochizuki, tudo jóia? Parabéns aí pelo evento.
Obrigado, Shida. Obrigado por estar aqui com a gente, Cristiane. Bom, acho que a gente já pode começar. Share the screen. Bom, pessoal, muito obrigado pela presença. Eu agradeço o apoio da Comissão de Pós-Graduação, do Programa de Pós-Graduação em Ciência da Atividade Física, das clínicas MO, Fisioterapia e Fisiopass, que também nos deram suporte para que isso acontecesse. É uma honra, né, estar apresentando, né, o professor Joseph Hamill, que vai conversar conosco hoje, né, na sua segunda palestra, né, dentro do nosso seminário de biomecânica das forças internas. E Joe, thank you so much. O Joe, ele, só para comentar para vocês, né, o Joe já foi presidente da Sociedade Internacional de Biomecânica e presidente da Sociedade Internacional de Biomecânica. Então, são as duas principais sociedades internacionais da nossa área. Então, isso já indica o quanto que ele é importante, né, dentro da biomecânica. Também, eu vou tirar para ficar mais fácil, né, e agradecer né, o carinho que ele sempre tem conosco quando vem para cá. Joe, it's so good to have you here in Brazil. I know that it's not so easy, but I'm very thankful to have your friendship and your with us here. Thank you so much, Joe.
Thank you, Luis. And this is, I don't know how many times I've been in Brazil, but it's many, many times, and it's always appreciative coming here. I was asked to give a talk on computer simulation, and I was asked to base it on chapter 10 in research. And so there you go. And this chapter was written by Sandy Whittlesley, who at the time was a PhD student of mine, and who has graduated and continued on a successful career. So the things that we hope to accomplish in this seminar is learn how to use simulation in biomechanical research, learn the general procedure for creating and using simulation, discuss control theory, learn the limitations of computer simulations, and discuss examples from human movement simulation. I wanted to start off with a very simple situation. Mechanical modeling is nothing more than a representation, or actually better, an approximation of a mechanical system using mathematical formula. And this is a simple example of a population. In this case, this shows how a population of animals will change over time. So this is the equation right here. This is the equation right here. And you can see n represents the number of animals, and is the population growth, and 1 minus n is the decay. So when we solve this, we get n versus time, the number of animals versus time. Starts off very small, grows, and then tapers off. So you have a period of rapid growth. It's a very simple simulation. It does not account for anything other than the growth of the number of animals. Now, we can make a more complex model that would explain the underlying reasons for the change in the population. For example, the lack of vegetation, disease, influx of predators, and whether there's a misbalance in the number of males and females. So, modeling can be divided into two categories. I mentioned this very strongly yesterday, and I will mention it again today. You have physical modeling, and then you have behavioral or mathematical modeling. Physical modeling is like when you would actually use a model of the structure. Engineers might building a bridge, and you actually need a model of the bridge. So, like a scale model of the bridge. Behavioral model is more abstract in that all it describes is the behavior of the model. Okay, and all it developed from this is a set of equations. And the set of equations will describe the behavior of the model. Now, behavioral model is a process to enhance our understanding of human movement. And modeling is both enormously powerful, but it's greatly limited. This is what it looks like in terms of a flow diagram. You have a research question, you create a model, you write a computer program. If you have a simple solution, and it doesn't work, you go back, change this, and come back down here. So let's say you actually get it to work. You collect some data, you compare the model and the experimental data. If there's a good comparison, you make predictions. If there's not, you go back up here and change the model again. If you can make predictions, are the data interpretable? That is, can you make sense of the data? If not, you have to go back and change things. If yes, you've answered your research question. So it seems like a very simple process, and by the most part, it is a simple process. Most people fall apart at creating the model and programming the solution. So the key thing is to start off with a question, and it has to be a good question. All studies start with a question. Without the clear question, the model, it doesn't mean anything. The model depends upon your good question. And what happens, the model must start with a particular question so that you can develop the relevant parameters that control that question. This is an example. I use cycling here. One of the questions you could ask is, what is the effect of body mass when climbing up a hill? Or how does the activation of two joint muscles change between cycling on level ground or riding up a hill? Those are reasonable questions. Now, you have categories of human movement simulations. The first thing that and you've probably done this in your studies previously, the first category is rigid body segments or rigid body models. I mean, if you've done anything in biomechanics in terms of the calculation of joint moments, for example, we use rigid body models to do that. The other thing that we often use is a mass spring model. And generally here you have more than one mass or one or more masses and one or more springs that are linked together. And there are predefined equations for this. More complicated becomes wobbling mass models. And this has only been used by several researchers. But for example, if we were looking at joint moments, well, joint moments ignores the wobbling masses. That is the movement of the muscles up and down as the person moves. And then you have mass spring damper models. The addition here is a damper added, and a damper, it modifies the action of the mass spring. And then finally, we come to musculoskeletal models. And these have rigid segments, but rather than the moments at each joint, they have submodels of individual muscles. And most of these muscles would be modeled as hill-type models that we talked about yesterday. So why do we simulate human movement? And this is a very, very good question. The best way, obviously, would be to collect data. Okay, but sometimes it's really hard to collect data, the kind of data that we want. And so what we have to do is we have to generate data. And the most general answer is that humans are so complex and they have so many intrinsic limitations that we really can't collect those types of data. Humans are randomly variable, they're subject to fatigue, have limits of strength and coordination, and must be treated with due consideration for safety and ethics. Well, you don't have to worry about a mathematical model. You know, it won't get tired. It certainly will do the same thing for you every time. Okay. And so a computer model eliminates all of these constraints. So it's a good tool in that regard. I'm just going to give you a couple of examples here. Suppose we wanted to determine the best position to perform an athletic task. And in this case, a takeoff from jumping. This was a study by my colleague, Graham Caldwell and Scott Selby. And in order to answer that question, you would have to do many trials on many different postures. Okay. And for this study, the best single subject performance had to be collected before the subject fatigued. You can't do that. So Selby and Caldwell, they used a simulation to examine the best jump performance, modeling 125 initial takeoff positions. You couldn't do that with a human subject. This is actually what they found. This is the optimal height over all of these positions, the 125. And these are the muscle onset times that they got at the ankle, hip, and knee. And from this, you could pick out, well, what are the best postures? And then, of course, what you could do is then take these best postures, maybe 3 or 4 of them, and then use a human subject to see if they, in fact, were the best postures predicted by the simulation. Other uses of simulation that have quite often used now are virtual surgeries. And virtual surgeries are the surgeon would practice virtually the surgery that they're going to do so that hopefully they don't make any mistakes. There's models that evaluate risk to workers. Military paratroopers training for landings from a specific height used to simulate the safest height for such landings. Actually, paratroopers, 12% of all paratroopers during any one jump get injured, which is a lot. Models to allow research to experiment with conditions that cannot be tested, as was shown in the Selby and Caldwell paper. Or changing a single parameter in a model to test the effect of that parameter. For instance, if you were interested in determining increased elbow strength, you can change the model thrower very slightly. You know, change the starting position, change the middle position, whatever. So you can do a lot of things with simulation. This is one that I spoke a little bit about yesterday, but one of our students, Ross Miller, and I did this, and this was our model. This was the diagram of the model. This wasn't the equations that we actually used, but this was the model. It had a trunk, a thigh, and a calf, and a foot. And what we did, when you are trying to simulate something in the model, you give it a cost function. And the cost function is simply, these are the conditions that you must follow. And in this case, we asked the model to run in 3 different conditions. First of all, at the most energetically efficient way the model could run. And what we found, the model always ran with a rear foot strike. Next, we asked it to run as fast as you can, as efficiently as you can. And it chose what we would refer to as a midfoot strike. However, it did increase the cost of running. This was the rear foot cost. This is the midfoot strike cost, which is an increase of 1.2 kilocalories per minute. And lastly, we asked the model to do nothing but run as fast as you can. Don't care about energy at all. And it always chose a forefoot strike. So this is the kind of thing that you can do with simulation. And like I said, we actually tried to do this study on humans, but the problem was that rear foot strike, changing to midfoot strike, changing to forefoot strike are not a normal procedure for a human to run. You don't normally change your footfall pattern. So the general procedures for simulations. It's a computer program. So if you're not a computer programmer, it's difficult to do a simulation. And what you do is you create and diagram a mechanical model, whatever the model is. If it's a runner, you normally would outline like a runner. And you define the equations of motion for the mechanical model. Okay? You program a numerical solution for those equations. And you determine, and this is most important, starting and ending positions for the simulation. Now, for example, in our running simulation, it started when the foot touched down on the ground, and it ended when the foot left the ground. Okay? So then you would run the program and you would generate model kinematics. What you would then do is interpret the model and compare them with the experimental data. If you had experimental data, you might collect it afterwards, but you have to compare it. So the very first step that you would do is the free body diagram. And like I said, you've probably done this in any biomechanics class. And a free body diagram is just a visual aid for deriving the equations of motion. Okay? So what you have to do is, how many components will the system have? And we talk about, like we had 4 components: a trunk, a thigh, a leg, and a foot, and a foot. Then you have to decide, is it a 1D, 2D, or a 3D model? Obviously, 3D models are more complicated than a simple 1D model. How many coordinates, that is degrees of freedom, are needed to locate each of the components' positions in space? And are there any means to reduce the number of coordinates? You know, the fewer coordinates you have, the easier it is to do. Okay. If you have multiple coordinates, you know, like if you have 50 or 60 coordinates, then it gets very complicated. And of course, the complexity, how intricate the model is, depends on how you answer each one of these questions. Okay. Now we talk about system complexity. A 1D model has been used many, many times to study locomotion. We did this, Ken Holt and I did this in looking at stride length, stride frequency. One of my former students, Tim Derrick, and I did this study. We looked at modeling the foot ground impacts during running. Mizrahi and Suzak did the deformation of the leg during running, and the influence of the viscera on breathing patterns. Minetti and Belli did that. These are all good questions. And, you know, and appropriate for a 1D model. 3D models are less common because they're very, very complex. Fred Yaden at Loughborough University in England, he does aerial movements in diving and gymnastics, and he uses 3D models, very complex. So the complexity depends upon your answer. So if a model has n components, you know that each component requires k degrees of freedom. So there will be n times k equations of motion. But then what you do is you put on constraints to try and reduce the number of equations. Okay. So let's say you had 4 components and you had 2 equations for 2 degrees of freedom for each component. That means you will have to have 8 equations and so on. So you can see how this could get more complicated the more components and the more degrees of freedom that you add. Now, I'm going to go through one that Sandy Whittlesey and I did, and it was a compound double pendulum, and we were trying to model human running. Now, compound double pendulum is, it starts off okay, but then it becomes chaotic, and we had to control for that. So what we had was 2 components, a thigh and a leg. The motion was each component moves linearly and rotationally. So the component would move linearly and it would rotate. And our coordinates, each component requires an XY coordinate and an angular position to define its space. So here you can see the XY position of the center of mass of the thigh and this angle that completely defines its orientation in space. Now, and we did the same thing obviously for the leg here, but the constraints, and this helps us reduce the problem significantly. The leg must join the thigh at the knee, okay, right here. Wherever the thigh is located, the coordinates of the leg center of mass is a function of the thigh center of mass, the thigh angle and the leg angle. Okay. You see that defines the system. And what we can do then is we can completely describe the position of the system with 4 coordinates: the XY position of the thigh, the angle of the thigh, and the angle of the leg. Okay. Now, what we have to do in simulations is we have to describe how the positions in the system change over time. And specifically, the motions of the segments are described with differential equations. That's my phone, by the way, but just leave it. It'll go off. A differential equation, this is an equation that you're probably very, very familiar with. And this is the differential equation based on this. And if you look at this, this is basically the second derivative of this. That's all that is. That's all of the differential equation is. And what you can do in this is every kinetic factor alters the movement of the body, and it must be expressed in the form of a differential equation. Here, this is gravity. And the initial conditions are the initial position of x and the initial position of velocity. So what we did for this compound pendulum, we developed a set of differential equations. And these are the differential, this is the differential equation here. This is the length of the leg, sorry, this is the length of the I think this is the length of the thigh over the length of the leg. And here is the mass of the system, the mass of the leg, the distance that the leg travels. And then we have all of these defining each, and this is a long equation, it just added together. This determines the thigh, and you can see the angle of the leg and the angle of the thigh. This is the angular velocity. This is the linear acceleration of the hip, and in the x direction, and the linear acceleration of the hip in the y direction, and including gravity. So, sorry, this is the sum of the moments. So, I mean, you need quite a high degree of mathematics to develop these differential equations. But the way we actually did it was in a simpler way. You know, there are multiple, you know, we always calculate everything in biomechanics using a Newton-Euler approach. What you can do is there are other approaches. And what I'm going to talk about for a moment is called the Lagrangian approach. And then, you know, you can go even further than that. There's a Keynes approach. But like I said, the easiest one to do simulations in, I think, is the Lagrangian. And unlike Newton's equations, it uses the mechanical energy of the systems. So here is the derivative of the partial derivative of kinetic energy over velocity, linear velocity. Here is the kinetic energy over the y position. These are partial derivatives. This is the potential energy, and this is the y position, and this is the total force that is generated. So this is just a different way of doing it. And if we did this using Newton-Euler, and we did it doing Lagrange, or we did it during Keynes' method, we would get exactly the same answer. It just means which is the easier way to do it. So this is the angular form of Lagrange's equation. Okay. And these are the moments to calculate the moments. And this is the one, the angular version of Lagrange's is the one that's most often used. And to implement these equations, it's all you have to do is establish the degrees of freedom to completely describe the position of the system. And in general, the angular coordinates to describe the segment's position and one linear coordinate are all you need. So this is trying to diagram this. This was our free body diagram. Okay, we had another segment down here, but I'm just going to show it with one segment. And the position of the pendulum can be completely described by one angle, this angle. And, you know, which for our convenience is reference to the vertical. You can turn this upside down and do the same thing. So the pendulum has a mass of m, a moment of inertia, I, about its pivot. This is the pivot here, and the mass center location D, which would be right about here. And so these are the energies of the system. And then we put them into a form of partial derivatives. And when you look at this, it all turns out to be this, and you have I alpha, where alpha is the linear acceleration. Now, we have different techniques for solving these equations. You know, generating a model is it's a complex process, and you have to have a way of solving those equations. Now, presently, you can solve those equations very, very easily because most people will use a program called Mathematica. Mathematical will solve the equations for you. You don't, if you look in, or if you have a copy of the research methods in biomechanics, Sandy and I wrote all of the equations to solve this problem that I just showed you. And the equations cover at least 4 pages of just equation after equation in order to solve them. Mathematical will do this for you in a matter of minutes. It doesn't teach you how to do it, but it will do it for you. Now, normally what you have is the current position, velocity, acceleration used to calculate a new position, new velocity. And what I'm going to show you here, I will use an example before I'll go to this graph. Most of you watch the news, and with the news, you get the weather report. Okay? The weather report is nothing more than a simulation. The simulation shows the weather tomorrow and the next day. It's pretty good. It's a very good simulation. It will give you very accurate results. If you take that out to next week, the results get bad. If you try to go the next month, they're really, really bad. And that's exactly what happens in a simulation. Okay. When you start off with this initial velocity, and even with a change in velocity, your positions are accurately reflected here. But then you get out to here, and they're not reflected at all, but they're reflected very well in a limited range. Okay. This is true of all simulations. And this is why, for example, when we were doing the running simulation, we had a very short period of time from foot strike or foot contact to a foot takeoff. If we had tried to go 3 or more steps, the model would probably fall down. So in the numerical solution techniques, you have what we call an analytical solution to the differential equations. And this can be derived, and all it does is give you the solution equation for this. A numerical solution is developed using numerical values. And this is an iterative process. It just goes through and iterates through the equations to give you a solution. So here, you start off with initial equations. Then you have your differential equations, your next condition. Does it meet the end condition? No. Then it goes back and does this again with new values. Okay. If it does meet the initial conditions, then it's over. Okay. So what happens is initial conditions, you solve here, you get the next conditions. These next conditions, if they don't here, if it's not used here, then these next conditions are used here. And they calculate another set of next conditions, which are continually cycled until you meet the end. You know, for example, an important part of a numerical solution is determining the starting and ending. Where do you want to start? Like I said, in running, we started when the foot contacts the ground, ending when the foot leaves the ground. When you're simulating a jump, the logical starting condition would be the initial posture. You know, this posture to jump, maybe your starting conditions. And determining the end conditions sometimes is not as simple, because the exact position of the simulated body becomes less and less predictable as the simulation proceeds. So it's good to have a definitive end position. You just can't let it go on forever, but it will. And so a robust algorithm has to be determined for properly ending the simulation. Like in terms of the jump study by Selby and Caldwell, their starting position was the initial posture. Their end position was the highest jump height achieved, or the, you know, Okay, that was a very simple entity. So what I'm going to do is I'm going to show you one method that can be used in this iterative process. And this is called the Euler method of integration. I don't know if you're familiar with Leonhard Euler. Leonhard Euler was a brilliant mathematician in the 18th century. And he has so many mathematical equations named after him that it's hard to keep them all straight. But this is the mathematical method of integration. And this is basically, or can be used for a simulation. Unfortunately, when you try to use this, it's very slow in terms of computer time. So the equations used in the Euler method are for a mass spring model. And a mass spring model is just a mass on top of a spring. Okay. Or it could be a spring hanging down and a mass in the bottom. It doesn't matter. And this is the differential equation for that. This is the spring stiffness, mass, gravity. This is where the position you're trying to predict. This is the initial position in the y direction, and this is the acceleration in the y direction. Okay? So you have a lot of unknowns here. You also have a lot of known things. Like, for example, you know the stiffness, you know the mass, you know gravity, you know the initial y position, and you know this position as well. So what you would do is you integrate this equation and you get this. And then you integrate this equation and you get that. Now, how do you use it? Well, like I said, we know a lot of things about this first differential equation, that one. We know the initial position. We know the stiffness, we know the mass, we know that, we know that. And then we try to solve for this. So what we do is we solve for this and we get this, and it goes into this equation. Okay. And then you solve that equation, you know the initial velocity, and you know the time. Okay. And you get a new velocity. Then you integrate that equation and you use the new velocity here. You use the acceleration the y direction here, and you know everything else. And you solve that. That's the first time through. That's the first iteration. Okay. So then what you would do, you solve and get this new position, go up here and plug it in here. And then you solve again, differentiate, solve again to get the new velocity, integrate, solve again to get the new position. And then you go back again and do this over and over again until you're finished, until you define the end position. So here's what it looks like. This is a mass spring model. Mass, this was set up to make it easy. 1 kilogram mass, 40 Newton divided by meters of stiffness. The initial y velocity was -4 meters per second. The initial position in y was 1 meter, and the delta t, that is the time step that we're doing this, is 1/100th of a second. Okay. Now, I'll tell you right off the bat, the shorter the time step, the better your predictions will be. Okay. But for this purpose, 1/1 of the second is fine. So this is the first iteration. And you can see I plugged in all of the values and solved for the acceleration of y. Now, if you remember what g is, the acceleration due to gravity, the change in that first time step is not very much. It's only falling a very small amount. So what we do is then plug everything in to the second equation and integrate it with all of this is the t now. This is minus 9.81 from here. And minus 4 is the initial velocity here. And we get this new velocity, and it's now minus 4.1. You see, it's actually negative a little bit. The velocity is a little bit greater. Now we use the third equation, which has been integrated. And what we get now is the new y position. You see the initial y position was 1 meter. Now it's fallen 0.042 meters. Okay. So we go on to the second iteration. We do exactly the same thing, but we're now plugging into this, all of the new parameters that we discovered from here. You see 9.85 is the new position. And we get now an acceleration of 8.17. You see it's slowing down a little bit. We get a new velocity now of 4.18, which is a slightly higher negative velocity. And we solve for the y position, and we get 0.916, where it started off at 1, it went to 9.58. Now in the second iteration, it's down to 0.916. And so this would go on and on and on. And of course, the ending position that we put was when y gets to 0. Stop the simulation. And so this is what it looks like. Well, as it turns out, the height starts off at 1. It never really gets to 0, but it gets close to 0. Okay. And then it will rebound up. Okay. We can actually do the force calculations from this, and the force looks like that. And these are exactly what you would predict for a mass spring that you release and let it bounce back up. Okay. So that's the Euler method of integration. There's something in terms of all of this that we have to take into consideration, and that is control theory. You should note that there are many, many ways of modeling forces and moments. As the body becomes more sophisticated, we begin to model how the body controls itself. We're really interested in control here. And control theory is a branch of engineering that studies the control of systems, both man-made and natural. And for example, how does an autopilot fly a plane? Okay. How do regulators, focus on changing the temperature or keeping the temperature at a certain level? How do anti-lock brakes work? These are all control theory problems. And human movement researchers have explored the means by which a particular task is controlled, and it draws the information from the engineering body of knowledge on control theory. And one aspect of control theory that is of great interest is feedback. Most of you are familiar with, feed forward or feedback, and both are used in simulations. But feedback is the information collected by the organism about itself for the environment, and then it's fed back to the human in order to change something or keep everything the same based on that feedback. So there are many different forms of feedback that we receive: sensory, proprioceptive, proprioception, or haptic. This type of control is referred to as closed loop control. If a pre-programmed routine is enacted without using feedback, it's referred to as open loop or feed forward. Okay. It doesn't use at that instant the information that it has gained. And typically researchers program the model controls in advance, run the simulation, and then change the controls afterward. Okay, as I told you at the beginning, there are limitations to computer models. No matter how sophisticated the model is, there are still a number of factors that you have to consider. And you have to also understand that the model will never truly represent what you're trying to model. You know, you can't do it, well, at least no one can do it as to this day. So what you will have numerical imperfections. Okay. In some situations, you say, oh, at 0, stop the, stop the simulation. But you may never get to 0. And it may be beyond 0, or it may be before you get to 0. So you have these numerical imperfections. One of the other difficulties is modeling impacts. This is very, very, very difficult to model impacts because of the sudden change in the state of the system. Another is the approximation of complex human structures. Even in a muscle, you think we can't model everything about the muscle. We can't model, we can't model all of the elasticity of the. We can't model how the contractile issues. We can't build a model that truly exactly represents a muscle, because remember, even the Hill model doesn't do very well with eccentric contractions. You have a problem with the adaptability of the human system. Luis and I were talking about this last night. Humans will adapt to all situations. An example was something that I tried to do a long time ago. I had people running in very, very, very soft running shoes. And I had people running in very, very, very hard running shoes. Now, you would think that in the hard running shoes, the ground reaction forces would be high. In the soft running shoes, cushiony, they would be low. That's not what happened. In fact, what happened is the forces were the same. Why were they the same? Because the humans adapted. They changed some of their kinematic processes, namely knee flexion, to equate all of the ground reaction forces. And of course, you have the inevitability of having to make assumptions, because you can never account for all of the human and environmental factors. You have to make assumptions, no matter what you do. Now, we can assume that numerical errors are small and can be resolved. However, models are becoming increasingly sensitive as the number of components increase. So you have small errors that arise early, and they can propagate and become large errors by the time you end the simulation. And this is why, simulations can't go for a long period of time, because if you have those errors, they will propagate, and by the time you get to the end, you get junk. So models can have parameters that differ by many orders of magnitude. A model then is referred to as a stiff system of equations or rigid system of equations. And this can lead to a sensitive model. And this type of model generates inconsistent results. Impacts are very, very difficult to model because of the sharp changes in acceleration before impact, contact, and after impact. And also, you have these wobbling masses that have to be accounted for. And impacts generally violate the assumption that the human body consists of rigid segments. They don't. Even the tibia and femur will bend slightly. It's not completely rigid. And this is the big thing here. Human structures are infinitely more complicated than the model. Okay? For example, joints are not pivot joints, and segments are not rigid. So when you're modeling, remember that we're modeling and simulating a human system in which the sensory and control systems are super, super complex. So every model is nothing more than an oversimplification. It's an oversimplification. The extension of that is what you get in your answer is nothing more than an approximation of the reality. A good model will give you a good approximation. Okay. So this is one of the take-home messages. You have to be very careful in deciding how much a model says about the real world. The beauty of simulation is it's flexible and it's controllable. But it's still very difficult to draw inferences to the real world. All conclusions are implied, and they're always subject to further examination. My colleague Graham Caldwell used to say to me all the time that your model is never finished. You may use it at a certain instant in time, but you're continually refining it. So when we're interpreting a model, we have to consider the exact magnitudes of the quantitative data, treat it conservatively, because it's sensitive to these assumptions. Analogies between model and human structures should remain very loose or not at all. And never state that the way the model works is the way in which a human system works. Always discuss the model and humans separately. This is what I said yesterday in the Hill model. There's no structure of a parallel elastic component in the muscle. We use a mass spring model to define many things in human movement. There are no springs in the human body. There are things that act like springs, but there are no springs. And they're not as linear as a spring. They may act like a spring, but they're more nonlinear. These are a couple of examples that, going from relatively simple, computer models. This model had 3 segments, a straight representing the human body, a stance limb, and a swinging limb. And you know, the model had no muscles, and it started walking at the instant of right toe off. And you see this quite often. If you go to YouTube, you'll see this ballistic walking model, and it could only walk downhill. It could not walk on a level. And downhill, it was using gravity to keep it going. But it, you know, it did, you know, there's, you know, some interesting things you can gain from this. The model's walking speed was limited in order to clear the swing leg. Because if you walk too slowly or too fast, it would hit the leg and fall. And this is David Winter, his model for human locomotion. But now, if you notice here, what he had was including joint moments. And it looks similar to the model, but it was actually much more complicated. And if you notice here, it was using Lagrange's method. And he had 22 anthropometric constraints, or constants rather, in dozens of terms. So,
Obrigado. Ficou ótimo.
anyway, the simulation had 4 separate programs.
Oi? 55.
Run by a master program. Now, this is one that my student at the time, Tim Derrick, did. And we were trying to do the modeling the stiffness characteristics of the human body while running with various stride lengths. And in this particular model, this is the complete model. This mass represented all of the mass of the body with the exception of the stance leg. So the stance leg was eliminated from M1. Now, on the other hand, M2 represented the mass of the stance leg. We had a spring that represented the spring for the rest of the body. And then we had a spring for the stance leg, but we also had a damper. And what the damper did was basically to cushion the impact. And of course, this is easy because we actually collected experimental data on this as well. And we had the subjects running at different stride lengths across a force platform. And what we did was generated force curves from this model that looked like this. And then we compared them to the force curves of the person who actually running across the force platform. And in fact, they look very similar to this. Not exact, but close. I wanted to show you just the mass spring model, that this is what you get. And you notice that the mass spring model does not give you an impact. Okay. Now, this is what we get in a forefoot runner and a rear foot runner. Okay. The difference being, even though you don't see an impact peak here, there is an impact, but it's just melded into this whole structure right here, this vertical ground reaction force curve here. Okay. So, like I said, this is it's not a super complicated model, but it is complicated. And we, in this particular model, remember I said that the time, difference was very important. In the previous model, the simple model, we used mass spring model, we used 1/100th of a second. In solving this model, we used 1/10,000th of a second. Each step occurred at 1/10,000th of a second. Now, I'm going to try and summarize a lot of this. I didn't take a break today. I'm just going to go right through. Okay. So you should be pretty familiar with this. This is the inverse dynamics workflow. You start off with positions from markers or whatever. You have a kinematic analysis. you get angles, you doubly differentiate these angles and you get accelerations. You add in forces and masses and moments of inertia, and you get joint forces and joint moments. Okay. Most biomechanics students can do this now. A technique that we use called static optimization follows a very similar workflow with one exception. You get the joint moments and joint forces, and you add them in here. And what we could do using static optimization is get muscle forces, the bone-on-bone forces, and in fact, ligament forces. That's if you want to know what these particular forces internally are doing. So the joint moment and the joint forces, these are the resultants. And what we want to do is add stuff to this. We want to add the inertial forces, the gravity forces, and any external forces. And physiologically, we want to add in passive and active structural forces. That is muscles, bones, and ligaments. Now, we have some misinterpretations to start with. The joint forces are not the bone-on-bone contact forces. The moments are due to muscle forces. You can't tell individual muscle forces, but you can tell whether they're flexor forces or extensor moments. The problem is, many times you want to know these, and you can't get it from this. So you have to do an optimization. And the one that we're going to use, or I'm going to show you, is called a static optimization. What a static optimization does is it solves the problem at one instant in time. Goes the next and solves the problem in the next instant in time. So it gives you a digital result rather than an analog result. So I'm going to show you the thought process that goes into this. This picture here is from a very famous journal article by Crowninshield and Brand. So this is a model of the D. And what we have is 10 muscle forces, 4 ligament forces, 2 bone-on-bone contact forces, and they're all vectors. Now, if you remember back to your days in mathematics, you need, for every unknown, you need a new equation. So here, we have 42 unknowns. We need 48 equations. We don't have 48 equations. All we have is 6 equations, and we can only calculate 6 unknowns. So in this case, we're stuck. Where do we come up with the other 42 equations? These are the actual equations. This is the muscle force. This is the moment arm for all of the muscle forces, the bone forces, moment arm for bone forces, ligament forces, and moments arms. And all of this totals up to the moment at the knee. So what do? We have more unknowns than equations. That doesn't happen. We can't do that. We have lots of extra muscles too. So what we do is, and if you think about one approach to doing this, is we have Bernstein's degrees of freedom problem. And this described the fact that there is a redundancy in the system. There's also what's called the general distribution problem. How do you distribute all of these muscles into single forces or groups of muscles into forces? And then you have a force sharing problem. So now I'm going through, how do I narrow down my problem? So I'm trying to simplify it. It's still the same problem. I'm going to assume that the ligament forces are much, much, much smaller than the muscle or bone forces. And if that's the case, I can get rid of them. I don't need an equation for the ligaments. I can assume that the moment arms for the muscles are much smaller than the moment arms for the bone. Or sorry, much larger than the moment arms for the bone. So I get rid of the bone forces. So now I'm just simply left that the moment, the net moment at the knee is equal to the sum of the moments generated by all of the muscles. Okay. And, you know, I know the moment arms for the, for each of the muscles. You can get those from cadaver studies or musculoskeletal studies or other models, or you can actually look them up. They're in the literature. So you see, I've eliminated a whole bunch of equations. I'm trying to simplify it even more. So now we have 30 unknown muscle force vectors. And we can estimate the lines of action. So now we're down to 10 unknowns. And how do we get down to 6? Well, we could say that there are periods of muscle inactivity. And so I can eliminate those muscles. I can lump muscles together. So instead of having the 4 quadriceps muscles, I can say, well, let's lump them all together into the vasti muscle. And this is called a reduction approach. And you can see where I could start off with a model with 48 unknowns and 48 equations down to 6. Now, of course, this is making my model less complicated. And maybe I can only generate, small points of insight into the particular problem. So in optimization, what you generally do is you minimize or maximize a function. And the terminology that we use, J is used, and these are not mine, these are what are standardly used. J is the objective function or the optimality function, or the cost function. X is what we call the design variable, and X star is the optimal solution. Now, I have constraints, which further reduces the problem. I have an equality constraint. That's H equals 0. I have an inequality constraint here, which is less than or equal to 0. And then I have side constraints, a lower boundary and an upper boundary. So the lower boundary means what is the lowest force that the muscle can output? The upper boundary is what is the highest force that the muscle can output. And what I've done then, I've reduced or restricted the solution domain by doing all of this. Now, here's the problem. I'm going to minimize J. So my function is this, given this equality constraint. And it's subject to this constraint and the upper and lower bounds. Okay? Now, I have to have some function. Okay, and to have synergism in the muscles, it has to be nonlinear. But when you make this function, it has to have some physiological relevance. You just can't put numbers in. And the most popular way of doing this optimization is by using the sum of the cube muscle stresses. And so what we do is we take the net moment, and the net moment equals the sum of the cube muscle stresses. And you can make that that equation, solve that equation. And what it does is it gives you then each individual muscle's contribution to the total muscle moment. Okay. You can see there's a couple of papers here that you should read if you're interested in this stuff. And then you perform a step-by-step analysis. This would be the free body diagram for this. So what you have to do is you have to acquire the joint moments, joint angles, and best to use all three joints. It's hard when you try to use just one joint. We have to acquire moment arms. We get that from the literature. And we use some polynomial fitting to match everything up in time. We acquire peak muscle forces from estimates of muscle size and from modeling the dynamic. And then if let's say we're interested in one muscle, well, actually, we wouldn't be interested in one muscle, we're interested in several muscles. This is one step. For one muscle requires one step like this. And the function in MATLAB is called fmincon. If I had 6 muscles, I would repeat this line 6 times, but with different parameters in there. So this is what you need for each step. You need the muscle forces. That's going to be the outcome, the cost. This is the file that goes in dividing the objective function. Your initial guess, you can't start with the thing at 0. You have to give it a guess greater than 0. These are not used at all. These are the moment arms. These are the moments. The upper and lower bounds of the forces of each muscle. The nonlinear constraints, you don't use this. And the algorithm options, and you just use this optimum set, which is just built into MATLAB. So, I mean, doing the static optimization MATLAB, if you have your joint moments already calculated and angles, with a little bit more work, you can generally do this very quickly. And this runs very fast in MATLAB. And this is called a static optimization. Okay. So that's the procedure for one time step. You do that for one time step, go back and then do the next time step and so on. And we generally do it from 1 to 101, which is 0 to 100% of stance, for example. And of course, you check your output. Is it reasonable? The magnitudes should be reasonable. The histories should be smooth, okay, because the data are smooth when you put it in. And what you can do then is take these data, and actually these data, if you use OpenSim, these data, the static optimization can be used right in OpenSim. It will do it for you. And you can calculate bone contact forces, whatever. So that's everything you wanted to know about computer simulation, but we're probably afraid to ask. And I've gone over it very, very quickly. If you're interested in using it, read some of the papers that I've referenced here. The chapter in the book is a really nice starting point. And what I've presented today is a really, I hope, a nice starting point for you. So any questions, I'd be happy to respond or try to respond.
The application of the models, and as we were talking, a model is a simplification. The comparison with experimental data to see if your model is how close is to reality. But the problem is that even when we measure something, we are still not reading what is the real nature. Considering this situation, even if the model is very simple, you think that we should keep going on models, even knowing that the measurements are still not measuring everything, or we should go to only describing things and forget about modeling and predicting?
Modeling and optimization and simulation, they all have a point in research. I tried to illustrate to you, for example, the best example is that Selby and Caldwell paper. That was a study that you could never do with human subjects, but it was a relatively simple model. And asked a good question. And what it did was the protocol for the model was such that humans could never accomplish it without, being fatigued, that the results would be meaningless. And so what that did is it narrowed down, it could have narrowed down a set of potential best postures that then could be tested on humans. So as long as you know the limitations of your measurement system and know the limitations of your model, then you're fine. I think it's worthwhile. And like I said, we can't go in, like some of the work that I'm doing right now on looking at the strain on the ACL. I can't go in and put strain gauges on people's ACLs, but I can model it and get a reasonable approximation. So, like I said, there's no panacea, certainly. But on the other hand, as long as you know the limitations of anything you do, then you're fine.
Joe, you said that something that is very important for you to start modeling is to know the start position and the ending position. But we can also remember that usually as time goes by, the experimental data and the modeling data usually probably are going to diverge. Yeah. Not always, but it's going to be something that may happen. So instead of defining an ending position, could we define a time and let it run until 1 second?
Yeah,
and then
your ending position.
but then we don't know the end position that we want to know. Then
no, your end position would be the position you are at the time you designate as the end of the simulation. You don't know that. I mean, when I say end position, it could be end time. That's not, it's you can do that. There's no problem. In the work that I've done, it's all been defined by positions. And like I said, the shorter the time over which it occurs, the event occurs, is you're more accurate than if you let it go a long time. As I said, our model, it was fine for the first step, and it was fine for the second step, and then the third step, it just collapsed.
Joe, very nice to hear from you again. Thank you for the very nice presentation. And you gave us a good example of how useful can be the simulation. And most of the students, they will never work with it, but they might be consumers of the results from the simulation. Would you mind to give us some examples that actually that you know that information that we could pick up from these simulations and use in practical life, like rehabilitation or fitness or something like that? Do you have examples to give to us, and so that our students can go and look for that and use it?
You know, as I kept trying to say, if you know the limitations of anything, of your measurement system or of the model, and keep that in mind, you can't take the model results absolutely 100% verbatim and say these are the real way this thing happens. And I would never do that. I mean, even if you never do modeling, whether it's muscle models or computer simulation, if you never do that in your career, I think you should still be aware of it, and I think you should still read about it. But you should also know the limitations of everything. I really can't think of a situation. Well, I mean, I guess a situation there where people think that the results of the model are exactly the way a human functions. You know, if you get a computer model that says, during a biceps curl, you should be able to generate, 10,000 newtons of force for the biceps. Well, you should have some awareness to know that that's not going to be feasible. So, like I said, even if you never use it, you're going to read about it, and you just can't take it. You just can't take it literally. Okay, because as I said, every model has its limitations. Some models have more than others. But these are all approximations at best. Yeah. Yeah, I mean, in that particular case, that's an easy example. The way, like for instance, as I said, I'm interested in ACL strain right now under certain conditions. The ACL has been widely studied, externally, where they've taken cadaver ACLs and measured the strain. And so, you know, while that's not exactly real life, our model value are similar to what you get from a real ACL. Now that's valuable information. Okay. If you can verify your model values by some other source, that's valuable. But the thing is, it's not exactly what the human will do. And believe me, you know, I'm not an expert modeler. My modeling is just based on the fact that I've read a lot of papers and looked up how to do things. You know, my student that I wrote the chapter with, Sandy, was a brilliant modeler, you know, and Tim actually was very much like me. During his PhD, he learned to model. You know, you can learn this stuff. And the beauty of a lot of this now is you really don't know how to write the equations or anything like that. Like OpenSim will do that for you. And if you write the equations yourself, Mathematica will solve them for you. You know, way back in the old days, we used to have to do this by hand. You don't have to do that anymore.
Joe, this question came from the audience, and they are asking, it's a little bit on this way. What is a good question in modeling, in your opinion?
Anything that requires, or you're interested in an answer, you can model just about anything. Now, the good question is it relevant? You know, and I gave a couple of examples in cycling there. You know, my colleague, Graham Caldwell, I thought it was a really interesting question, he was interested in cycling, and he was interested, how did the two joint muscles perform when you're standing up cycling versus your seated cycling as you go up a hill? And, you know, he has done a lot of work on two joint muscles. I've done a lot of work on running and walking. And so I was interested in some of the questions that you could ask in running and walking. You know, my former colleague, Brian Umberger, was interested in the energy cost of individual muscles during certain activities. And you can do that with modeling. You know, actually, Brian Umberger did, along with, I can't remember, Karen Gerritsen at Arizona, when he was at Arizona State University, they did a walking model of Lucy. You know, they took the skeleton and had it walk. I know some other people who have done, you know, walking models of chimpanzees. Why do chimpanzees walk the way they do? You know, so there's lots of questions you can answer. It's the relevance. And of course, is it important to you? But I can't tell you what's, you know, I can tell you what's a good question that I'm interested in. You know, the one question we're doing right now is with the ACL strain. You know, when you run, you're running straight ahead. But what happens when you start to change direction? Does that changing direction, does that impose an additional strain on the ACL? Because as the strain increases, sort of the forces on the ACL, and it's a possible tearing of the ACL. You know, and then, of course, you know, we model that to get the ACL strain. And then, of course, we're adding another component into that. How does perception affect all of this? Now, you would think perception and ACL strain, you know, they're not linked, but they are. Because you're working with a human system that perceives when to change direction. So, you You know, there's no bad question. You just have to see if it's relevant to you and can you do it?
Pessoal, alguém tem alguma pergunta do Zoom? Alguém quer abrir a câmera e falar? É um bom momento. Quem gostaria? Well, Joe, I have another question.
Okay.
Because I'm really enjoying modeling, and usually modeling in biomechanics, not in, let's say, in physics or other fields, when they model, they use modeling to test their hypothesis about how world is built or how to explain what we see. When we do modeling biomechanics, we want to understand what is happening with our experimental data. Usually, we still don't have some laws to explain why we are moving. But one very important question that we have is the degrees of freedom problem. And the degrees of freedom problem, the answer is coordination and synergies. But the problem of modeling is that when you set, for example, for optimization or minimization, you are preparing the model for one answer.
No, you're preparing for a family.
For a family of answers. But then, what is variability under this situation?
Well, this has been a problem that has not really been addressed adequately in modeling. Is we know that humans are variable, and humans are nonlinear, and yet we model everything as linear. How do you introduce variability into a computer program? Now, my colleague at Loughborough, Fred Yaden, is trying to do that. I don't know how far he's gotten because of COVID. I haven't spoken to him in a couple of years. But, you're right. Computer programs generally give you, if you alter the conditions just slightly, it'll give you a family of answers. But if you keep the same conditions all the time, it will give you basically one answer. And that shows no variability. And it's beyond me how to do that. That's a Nobel Prize for someone who's really smart. And it's not me.
Thank you, Joe. I think that the problem of variability, it is something that all of us are moving, trying to find answers for that. But also modeling is also important to understand what happens why people get injury, just like you are asking yourself about ACL injuries. And the other kinds of injuries that we see, or even when we talked yesterday about falling, because people try to predict falls. And I was wondering if we can, how could we, for example, use simulation to understand not one final problem, but for example, understanding learning.
That's not my area, but I know there are models of that people have proposed on how to learn. I know nothing about it. Everybody uses models. The weather is the easiest thing because that affects everybody every day. And people, all they have to do is realize that those models are just models. And I always find it interesting when people say, oh, I wanted to play golf next Saturday, but it looks like it's going to rain. But the odds are that it may not rain either, because of the time out from the model. The further you're away from the initial conditions, which are today's conditions, the further out, the more inaccurate the model becomes. But we use models for everything. Banks use models to predict the interest rates. Next week, or car manufacturers use models to predict when parts will fail. So modeling is with us, and it's something I think in biomechanics we just can't come to it sort of late. And I disagree with you. We do have laws in biomechanics. We have natural law. And natural laws can't be violated. So.
Joe, do you think that we are going to reach a situation when people is going to start using modeling, just like, for example, let's say for personal trainers or physical therapists, they get used to know how to use OpenSim. So instead of asking some research questions, they try to make some clinical questions, and that question is dedicated to his patient. So do you think that it's possible to answer individual questions to say, okay, if I do this, if I shorten the muscles, if I do that, what is happening to my patient? And then he compares and he use that information to support his practice in daily life activities.
Well, you can do that, but I hope people don't. I hope people don't do that. I think the problem is if you get someone who doesn't know the ins and outs of modeling, they may misinterpret. So modeling should be left to the people who can do it. That's all I can say is you could do it. Anybody could do the modeling, but it's whether you know enough to interpret the data correctly. And like I said, I'm not sure that a personal trainer, unless they have a lot of experience in modeling and in biomechanics, would do that.
Do you know that one movie, Ratatouille? Well, it's a Disney movie, and the idea that rats can cook, and one of the slogans is anyone can cook. Could we say anyone can model that? Probably knowing the basics. Sure. We just pessoal, alguém gostaria mais de fazer alguma pergunta? Franklin.
Mochizuki.
Sim.
Ushida, tudo jóia?
Fala, Ushida.
Eu gostaria de fazer uma pergunta para o professor Hamill. Professor Hamill, it's a pleasure to hear your presentation. Congratulations for the fantastic presentation. Actually, I'm not a biomechanics researcher. I'm curious about the biomechanics, but I have a question for you about how is it the possibility or the proximity of modeling and artificial intelligence as a tool for health or performance, sports performance. Thank you.
Well, modeling and optimization are intricate to artificial intelligence. They would use like a feedback type of loop where the information gained instantly will be used in the next step, or the next iteration for the in artificial intelligence. They're basically the same thing. It's just artificial intelligence is taking it. It uses. I shouldn't say the same thing. Artificial intelligence uses simulation and optimization. Okay. I don't know where Louise has gone, but I just wanted to say hello to my friend Daisy, if you're still there. Oh, jeez.
I know that Joe, não sei se todo mundo sabe aqui que hoje é aniversário do Joe. You know that today is Joe's birthday, and I know that Joe doesn't join a lot celebrate his birthday because sometimes he complains that he's getting older. But we couldn't let that without anything to do. So Joe,
Thank you.
yeah, you can join us. We can get together.
We can't give them all a piece of it.
Pessoal, agora vocês podem abrir as câmeras, né? E a gente, né? Tem um bolo para o Joe, né? Eu vou tentar agora fazer o seguinte.
Oh, some of them.
Uhum.
I was just thinking I'm celebrating my 40th birthday for the 36th time.
Bill, I never forget when I was in the class and I brought to you like a piece of paper, if you remember.
Oh, yeah.
And you told me that you was American.
Yeah.
And I was so sad. But now I brought you a wine.
I don't drink alcohol.
But okay, I brought you. I was wondering what gift to you. And then I tasted yesterday and you can yeah, you're right.
She doesn't drink alcohol
Oh
either.
my God. You can celebrate at the class at the apartment. Or drink with like
Quem quiser abrir o microfone para falar, aniversário do Joe. I know that because of me, Geronimo, and some other guys, we always say something about Corinthians. So we bought this jersey, like this jersey. We are asking people, so we are asking people to sign on Saturday. We're gonna ask more people to do. But this is not going to wear, but to remember that this is. Asking myself, which would be nice for Brazilian jersey, of Corinthians. This jersey is cool because for the celebration of 100 years of Corinthians. So this jersey was used to use by Corinthians 100 years ago. So this is something that you may not have.
No, I don't. Thank you very much. Although I told
Yeah, but
yeah. I told
aí meu pai também está aqui e quer ajudar a tirar uma foto.
It's interesting because I told you yesterday that I was sort of following Palmeiras.
Yeah.
Thank you very much. Thanks.
You're welcome. Vamos acender. Pessoal, então se vocês quiserem abrir agora os microfones para cantar junto com a gente, vai ser uma bagunça, mas tudo bem, faz parte. gonna sing the Happy Birthday, but in the Brazilian version. Then we can end by.
Oh, boy.
Vamos lá.
Pra você nessa tá aqui. Possível.
Congratulations.
Thank you very much. Thank you, everyone.
Então, vocês não vieram, vocês não vão comer bolo.
Mas tem boa para todo mundo. If you will not feel good, okay?
I remember those molecular formulas in mass. I did have one of them.
Oh, the cheese, the.
No, the thing, the top, the sweet ones. Yeah, I did have one.
Oh, yes.
No, I.
Oh my God.
I don't like Reese's, but these are very nice.
It is very, very nice.
I thought, well, there's interesting. Okay, you may find in the principle. For instance, one can be.
I actually, when we visited the Corinthians training ground, they gave me a Corinthians jersey. And I do have a Palmeiras jersey. Actually, I have a Sao Paulo jersey too. Yeah. When I was here for in the top, I bought a whole bunch of teams. So,
Renato, vem aqui comer também.
everyone's going to watch us eat these.
Pode chamar o pessoal lá na. We can try to box this cake and send to Donna.
Oh, God. It'll be ruined by the time it ever gets there.
Yeah.
I'll take a piece back to her, though.
Yes. Yeah, I know, Joe. I know, Joe, that you were trying to be on a diet, but I know that sweeties, you don't say no. You usually don't.
I'll take more insulin.
Why?
Okay.
Tem bolo? Hoje é aniversário da Márcia também, não é? Falei para ela vir pra cá também. Quero sim, eu quero. Sim. Uhum. Obrigado, Renata. Obrigado a vocês. Você pega?
Luis has a plan.
Tomorrow, well, tomorrow is still an open idea, but at least tomorrow morning, or 3, and then you can wake up late. Then we meet for lunch. Then the idea would be working a little bit on in the afternoon. And if there were someone available, then we can have dinner together. Then Saturday, we have the activities here until 10. Then we go. Then we're gonna have a barbecue. Oh yeah. We do the COVID before that. We go to the drugstore, and then we do the COVID before coming here, maybe by 8. That. And then we go for lunch. Saturday we're gonna have a barbecue. And then it's open because I don't know yet if we're gonna have tickets for the soccer match. Julio is trying to. Julio Serrão. Because Julio Serrão is a professor in the School of Physical Education, and he is the board. São Paulo, they create a scientific board to support their activity. É bom. Pessoal, com isso a gente termina, né, a palestra de hoje. Combina de encontrar de novo na semana no sábado, tá? Tá? A gente manda para vocês e a gente se encontra de novo no sábado de manhã. Tá? Então, obrigado a todo mundo. Tinha esquecido, a gente ficou comendo bolo aqui, esqueci de vocês. Tá? Então a gente volta a se ver no sábado de manhã. E quem puder, né, vir no sábado para assistir presencialmente, tá bem tranquilo, tem bastante espaço, né, tá bem controlado aqui. Tá, pessoal? Um abraço para todos. Tchau, obrigado.